What's up? What's up? What's up, Abe? Let's go ahead and talk about Chapter 7, which is all about the human population, right? We already went over everything from Chapter 6, which is all about wild populations and the population ecology of different ecosystems. So let's look into a little bit more about how these things impact the human population. Here you guys can see a graph that's showing how human population has changed over time. So think about this. This is pretty crazy to think about, but every 5 days the human population increases by roughly 1 million people every 5 days. All right, about 1.8 million infants are born and around 800,000 people die. Our human population has not always grown at this rate. All right, as you can see in the graph here, a few hundred years ago the human population was stable. Okay, if you look at the graph around right, deaths and births occurred in nearly roughly numbers. The situation changed about 400 years ago when agricultural output and sanitation began to improve, okay? We had better living conditions. That caused the death rates to fall, but our births remained relatively high still, all right? This was the beginning of a period of rapid population growth, which resulted in the current human population of almost 8 billion people. Okay, this isn't super updated, but it should be up here even higher. You can see the exponential growth right here. So just like in Chapter 6, what we learned about, under ideal conditions, all populations will grow exponentially. So in most cases, exponential growth stops when an environmental limit is reached. The limiting factor can be a scarcity of resources such as food or water. It could be an increase in predators, parasites, diseases, something like that. But these limiting factors are what determines the carrying capacity of a habitat. All right. So because humans are a little different, right? We have to think about the question, are human populations constrained by limiting factors as other populations are? That's what we're going to talk a little bit about today. So environmental scientists have differing opinions on our Earth's carrying capacity for humans. Some scientists think that we've already outgrown, or eventually we're going to outgrow the available supply of food, water, trees, fuel, and all the other resources that we have, okay? But one of the first proponents of the notion that human population could exceed our carrying capacity was this English dude named Thomas Malthus. All right, in 1878, Malthus observed that the human population was growing exponentially, but the food supply was only growing linearly, right? Eventually, the human population size is going to exceed the food supply. If you check out the graph here, you can see this. It's shown here. A bunch of environmental scientists today share multiple views that humans will eventually reach the carrying capacity, and basically after that, the rate of our population growth will decline. But other scientists don't think that the Earth has a fixed carrying capacity for humans because they argue that the growing population of humans will provide an increase in supply of intellect, right? We'll have more smart people if we have more people, and that will lead to increasing amounts of innovation and new inventions and technology and all that good stuff. So by using this creativity, these scientists think that humans can alter the Earth's carrying capacity, right? We can make more out of what we already have. But is that really going to happen? So if you look at this graph here, you can see how population size is changing exponentially, but we have this linear change in the amount of food that is available. So this is a more updated graph here showing what these scientists think, about innovation and stuff. You still see the exponential population going up there and that linear increase in food supply, but right around here is where our brains come into play, right? We have that innovation that actually moves the linear line up higher, so that maybe we can supply all the people that live on this planet food. So because humans are really, really unique, right, we kind of fall in that weird gray space. Do we really have a carrying capacity? What is it? How do we figure this out? Basically, there are so many different variables that go into this math that it's not really realistic to find a good amount. But this number right here is a number that was produced using the average ecological footprint of people all over the globe. So some scientists figured out that it's going to be, this is our carrying capacity, right? Somewhere in between 9 and 10 billion people based on how much we use right now. And that's including information on water, our ability to grow food, and our consumption of all these other resources. These are our projected world populations that were done by the UN, right? The United Nations, right? They expect that we're going to have around 8.6 billion people in 2030, 9.8 billion people in 2050, and 11.2 billion in 2100. Well, guess what? That number down here, the 11.2 billion, that's over this number, right? It's definitely over 9 and 10 billion people. So the other thing we have to think about is that over time, these developing countries, which are producing so many people right now, they're actually going to become more developed. We'll talk about the demographic transition model here in a little bit. But When developing countries become more developed, typically they start using more resources. So it's a big, hot, dirty mess that we're going to talk about. So the main thing we're going to talk about today are the 5 factors that drive human population growth. In order to understand the impact of the human population on the environment, we first have to understand these 5 factors that drive human population growth. Okay, so the study of human populations and population trends is called demography. That's a term you guys should be familiar with. And we call the scientists that study demography, we call those scientists demographers. All right? So these demographers analyze specific data like birth rates, death rates, migration rates, but they can offer insight into how and why populations are changing and what we can do in order to influence the rates of change. All right, so let's look at these different factors in a little bit more detail. Are you ready? So the first factor is changes in population size, right? The human population has a system with inputs and outputs, just like all biological systems. We talked about this a little bit last chapter. But if there are more births than there are deaths, the inputs are greater than the outputs, right? And the system expands. So you should recognize this graphic right here. For most of human history, our total births have slightly outnumbered the total deaths, which results in very slow population growth. But if the reverse had been true, the human population would have decreased and eventually we would have become extinct, which is a weird thing to think about. But when demographers look at population trends in different countries, they take into account the immigration of people into a country and the emigration of people out of the country. So just like we talked about in chapter 6, that means that the inputs to the population include both the immigration and the births, right? And outputs or the decreases include the emigration and the deaths. All right. So when the inputs to a population are greater than the outputs, that means that the growth rate of the country is going to be positive, right? If the outputs are greater than the inputs, the growth rate is going to be negative. Demographers use specific measurements to determine yearly birth and death rates. Okay, so there's this thing called the crude birth rate, or CBR. That's how we abbreviate it, right? The CBR is the number of births per 1,000 individuals per year. Pretty straightforward. There's another word that you should know, which is the crude death rate. That is the CDR. That's just the number of deaths per 1,000 individuals per year. So worldwide, there were 20 births and 8 deaths per 1,000 people in 2009. We don't usually factor in migration for the global population because even though people are moving from place to place, they don't leave Earth. So in 2009, the global population increased by 12 people per 1,000 people. We can write this rate out mathematically as this formula right here. Okay, it's going to be your CBR minus your CDR divided by 10. Even though the birth and the death rates are expressed per 1,000 people, we usually just divide this by 10 so that we can represent the value as a percentage because most people know what a percentage is. That's the reason why we do that. If we want to calculate population growth for a single nation, we have to take immigration and emigration into account. So it's basically the same formula, except you have to take your crude birth rate plus the immigration minus the crude death rate plus the emigration and divide that by 10. Okay, so it's really similar. You're just including immigration and emigration. All right. Don't worry about the intricacies of these formulas. We're going to do some practice with this in class. As you can see, the formulas are really easy. It's not like advanced calc or anything like that. But there is a little bit of math that you do have to know. The last thing, the rule of 70, right? If we know the growth rate of a population and assume that that growth rate is constant, we can calculate the number of years it takes for a population to double, which is known as doubling time. Because growth rates might change in future years, we can never determine a country's doubling time with certainty, right? We can say that a population will double in a certain number of years if the growth rate remains constant. But that doubling time can be approximated mathematically using this formula, what we call the rule of 70. So your doubling time in years is just 70 divided by the growth rate. All right, so let's look at some examples of crude birth rates. I just wanted to throw this in here because you might be thinking, well, what the heck? I don't understand. But anytime we have a number that's greater than 30, when we're talking about crude birth rates, that means 30 births per 1,000 people, right? Anything above 30 is pretty high. That means the population's increasing, right? Anything less than 18 is usually considered pretty low. Our global average is about 20. Germany is an example of a country that has a low crude birth rate, CBR, which has about 8. Niger has about 50. That's high, super high. The US is sitting at about 14. So this is a graph that's just showing the range of population estimates, right? There's way too many variables to come up with a really decent number about where the population might be. But scientists are thinking around 2050, right? We could be anywhere from 8 to 10 billion. It could be a lot higher, could go up to, by 2100, up to 11 billion or so. We'll talk a lot more about this in class. This is just a graph that's showing a similar thing, but it's showing what countries specifically or areas on the planet this growth is going to come from. So developed countries are down here at the bottom. We're not going to see a whole lot of growth from these developed countries. What happens is over time, and we'll talk about the theory of demographic transition, but over time as countries become developed, typically they have less kids and their crude birth rate goes down. Developing countries, however, have a higher CBR, and that's why this part of the graph right here is going up. Africa is projected to go up, China, India, all that jazz. We'll talk about that more in class. Let's talk about the second factor here, okay? It's fertility. To understand more about the role that births play in a population's growth, demographers look at the total fertility rate, or TFR is how we abbreviate that. Okay, the total fertility rate is an estimate of the average number of children that each woman in a population will bear. In the United States in 2008, for example, the TFR was about 2.1, which means that on average, each woman of childbearing age, right, who can have a baby, would have just over 2 children, 2.1, right? So unlike the crude birth rate and the crude death rate, the TFR is not calculated per 1,000 people. Instead, we just use it as a measure of births per woman. But to gauge these changes in population size, demographers also calculate replacement level fertility, okay, which is the TFR required to offset the average number of deaths in a population so that the current population size remains stable. So usually we call replacement level fertility just over 2 children, because 2 is the number of offspring that it would take to replace the parents who conceived them when those parents die. So any number higher than 2 is going to give you that replacement level fertility. But if your TFR is something like 1.6, that's less than 2, obviously, which means based on your birth rates, over time, the population is going to go down. So let's talk about developed and developing countries, right? In developed countries, or countries that have relatively high levels of industrialization and income, we're usually going to see a replacement level fertility of like 2.1. But in developing countries, it's a little different. We have relatively low levels of industrialization, and the income can be less than like $3 per person per day. In these countries, mortality among young people tends to be higher, and so they need to have a TFR that's greater than 2.1 in order for that country to achieve that replacement level fertility, because more people die when they're younger, right? But when TFR is equal to replacement level fertility and immigration and emigration are equal, a country's population can be stable. A country with a TFR of less than 2.1 and no net increase from immigration is probably going to experience a decrease because that TFR is below replacement level fertility. On the other hand, though, a developed country with a TFR of more than 2.1 and no net decrease from emigration is likely to experience population growth because that TFR is above replacement level fertility. All right, life expectancy, factor number 3. To understand more about the outputs in a human population system, demographers study the human lifespan. Life expectancy is the average number of years that an infant born in a particular year in a particular country can be expected to live, given the current average lifespan and death rate of that country. So you can see this graph right here. I guess it's a map showing the different life expectancy in years. Darker colors mean they're going to live to be older, 75 and above. Okay, so life expectancy is generally higher in countries with better health care, makes sense, but a high life expectancy also tends to be a good predictor of high resource consumption rates and environmental impacts. They all go hand in hand. Okay, so there's a graph right here showing these different life expectancies around the world. We often report our life expectancy in 3 different ways. Okay, usually it's going to be reported as first, the overall population of a country, second, males only, and then the third way we report it is females only. So for example, in 2008, global life expectancy was 69 years overall on average, 67 years for men on average, and 70 years for women on average, right? In the United States, it was a lot higher though, right? Life expectancy was 78 years overall, 75 years for men, and 81 years for women. So in general, human males have a higher death rate than females, which leads to a shorter life expectancy for men. So historically, men have tended to face greater dangers in the workplace, right? They typically would have more difficult, dangerous jobs. They make more hazardous lifestyle choices. I'm talking about statistics, okay? I'm not just making assumptions. And also they go to war, right? They're in the military, so the chances of them dying in a war is a lot higher than a woman. But these types of things are changing over time, right? Our culture has changed. So women are working similar jobs to men. There's a lot more women joining the military, et cetera, et cetera. So basically, demographers think that in the future, this life expectancy gap is actually going to get smaller. And that gap between men and women is probably going to decrease. Okay, I got a joke for y'all. What do you call a pig who knows karate? A pork chop! Isn't that pig just freaking adorable? Look at him right there, chopping the pork chop, chopping the brick. I mean, the availability of healthcare, access to good nutrition, and exposure to pollutants are all factors in life expectancy, infant mortality, and child mortality, right? The infant mortality rate is defined as the number of deaths of children under 1 year of age per 1,000 live births. Now, don't get this confused with child mortality rate, okay? They're very similar, but the difference is the age, okay? The child mortality rate is the number of deaths of children under age 5 per 1,000 births, okay? So there's a difference between the infant mortality rate and the child mortality rate. The dark bluish purple, those are countries that have 100 or more kids die under the age of 1 per 1,000 kids, okay? So that's really high. The U.S. is sitting here less than 10. But y'all can look at this. And this is something that we'll look at when we do our group project. So if a country's life expectancy is relatively high and its infant mortality rate is relatively low, we can probably assume that that country has a high level of available health care, lots of food, potable drinking water, sanitation, and they have a moderate level of pollution. Right. On the flip side, if its expectancy is relatively low and its infant mortality rate is relatively high, it's probably more than likely that the country's population does not have sufficient healthcare or sanitation, and that the potable drinking water and food are limited in supply. Pollution and exposure to other environmental hazards could also be pretty high. In 2009, the global infant mortality rate was 46. That's the average, right? In the United States, it was at about 6.6, so that's pretty low. But in other more developed countries like Sweden and France, they had even lower infant mortality rates. So in Sweden, it was about 2.5, and in France, it was about 3.6. So the availability of prenatal care is a really, really important predictor of infant mortality rate. For example, the infant mortality rate is 99 in Liberia and 50 in Bolivia, right? Both of these countries are countries where women don't really have good access to prenatal care. I don't have it written here on the slide, but another really important regulator of human population are diseases. Okay, so according to the World Health Organization, infectious diseases, especially the ones that are caused by microbes that are transmissible from one person to another, are the second biggest killer worldwide after heart disease. In the past, you probably learned that tuberculosis and malaria were two of the most infectious diseases responsible for the greatest number of human deaths. But today, the human immunodeficiency virus, otherwise known as HIV, which causes AIDS, is responsible for more deaths annually than any other tuberculosis or malaria on the planet. Age structure, factor number 4. We're going to be talking about age structure diagrams, population pyramids. Demographers use data on ages to predict how rapidly a population will increase and what its size will be in the future. So we have these graphs called age structure diagrams, and I'm going to show you these on the next slide. But they're visual representations of each structure within a country for males and females. All right, each horizontal bar of the diagram represents a 5-year age group. And the total area of all the bars in the diagram represents the size of the whole population. So let's look at these. Every nation has a really unique age structure, but we can usually group these countries into 3 categories broadly. All right, so a country that has many more younger people than older people has an age structure diagram that's widest at the bottom and smallest at the top. This type of age structure diagram we call the population pyramid. Okay, so this is really typical in developing countries like Venezuela and India. It's clear that there's really, really high growth at the bottom, but as you get older, you can see here it's going down. But basically this wide base at the bottom of the graph compared with the levels above it shows us that the population is going to grow very largely in the future because a large number of females aged 0 to 15 haven't had any babies yet, right? So even if each one of these future potential mothers has 2 children, the population is going to grow just because there are increasing numbers of women who will be able to give birth. So a country with little difference between the number of individuals in younger age groups and older age groups has an age structure diagram that looks more like a column than a pyramid, okay, from age 0 to 50. So this one here would be a good example of this. If a country has a few individuals in the younger age classes, we can basically deduce that it has slow population growth or it's approaching no growth at all. So the US, Canada, Australia, well, there's some other ones, Sweden, lots of other developed countries, they have this type of age structure. So a whole bunch of developing countries that have recently lowered their growth rates should start to show this pattern within the next 10 to 15 years or so. A country with a greater number of older people than younger people, like this one here, this is Germany, has an age structure diagram that resembles an inverted pyramid. Such a country has a total fertility rate below 2.1 and a decreasing number of females within each younger age range. Okay, so this population is eventually going to shrink. Italy, Germany, Russia, there's other developed countries like this. Denmark is one of those. These countries all display this pattern. China is in the very early stages of showing this pattern. So you can see it's a little different here because they have a lot more males and females in this age range from 10 to about 25, but it's kind of similar. So there's another term you guys should be familiar with, and it is this. It is population momentum. It's the reason why a population keeps on growing after birth control policies or voluntary birth reductions have begun to lower the crude birth rate, the CBR of a country. Oh, great night. Wow. Eventually, over several generations, these actions will bring the population to a more stable growth rate. The last factor is migration. All right. The net migration rate is the difference between immigration and emigration in a given year per 1,000 people in the country. If we have a positive net migration rate, it means that there's more immigration than emigration. Okay, there are more people coming in than leaving. If we have a negative net migration rate, it basically means the opposite. There are more people leaving than coming in. So, for example, approximately 1 million people immigrate to the United States each year, but only a small amount of people leave. Usually people immigrate to the United States, not emigrate from the United States. So our net migration is usually positive. This is another reason why our population is actually going up in the United States, because our crude birth rate is pretty low. But we have so many people immigrating to the United States that overall our numbers are increasing. Okay. So if you're ever wondering, oh, well, people are having less kids in the United States, why is the population going up? It's because so many people want to immigrate here, and they do. So yeah, that's why that's happening. So here are some examples that I wanted to show you, right? Here's the US. We have a positive net migration rate of about 3.3 out of 1,000. Fiji is a country where a lot of people are leaving, so they have a negative net migration rate. They have more emigration than immigration happening. So it's negative 8 out of 1,000. And obviously, the movement of people around the world doesn't affect the total number of people on the planet, but there's a lot of different reasons why this is an important issue in environmental science and why we're discussing it, right? Because with all of this movement of people, that's so easy to do, right? We can go get on a plane, a boat, whatever, and we can go anywhere we want nowadays compared to hundreds and hundreds of years ago. But this is a big deal because we're displacing all sorts of diseases, natural disasters happen, environmental problems occur, or so all sorts of conflict can make crowded, unsanitary conditions. It can make food and water shortages happen, massive amounts of people fleeing from other countries, creating refugee camps has an impact on all of this, right? All of these things can become very easily humanitarian and environmental health issues. Another thing that you guys have to think about is that this movement of people from developing countries to developed countries tends to increase the ecological footprint of these people, right? Over time, immigrants are usually going to adopt the lifestyle of the country that they move to. So, a person who migrates here from Mexico to the United States is going to more than likely use more resources here as a U.S. resident than as a resident of Mexico, because in the United States, we have a more affluent lifestyle. We use more resources. It's pretty simple and it makes sense. Here's your riddle for the day. What comes once in a minute, twice in a moment, but never in 1,000 years? Hey, you're the best. I hope you have an amazing day. Stay out of trouble, and I will see you in class.